Thanks very much. So I'm going to continue on from yesterday. So thanks everyone for showing up on the early in the morning on the last day. So where we left off last time was we'd introduced the two-channel Kondo model and where you can get it from in some real materials cases. And so now I sort of introduce the idea of over-screening. So just to refresh your memory, this is when you have a quadrupolar ground state doublet, which is then screened by two channels of conduction electrons and gives you an intrinsically degenerate two-channel Kondo model, which I'm telling you is intrinsically quantum critical when these two are equal. One of the biggest signatures of this criticality is that it has a 0-point entropy, which is allowed because it's an impurity. And this is 1/2 log 2. And this corresponds to a single Majorana fermion located at the impurity site. And so we'll talk about where this comes from in a second. I just want to remind you, Majoranas are real fermions. If you take two Majoranas, you can use them to form a single complex fermion, or you do linear combination of Fs to get Majorana fermions. So when you're looking at an impurity model, you can often solve this exactly. And so one of the ways you can do this in particular limit is what Emery and Kibelson did back in 1992, is they bosonized the problem. So any Kondo impurity problem essentially becomes a one-dimensional problem with your impurity and a conduction chain. So they bosonized this. These psi's are the conduction electrons. These F's are emergent fermions that are coming from the impurity site. And so you get essentially a conduction electron dispersion, which is linear here. And then you get a hybridization between your conduction electrons and your local Majoranas. So like they went through, they bosonized this, and then they refermionized it to get this picture. And these are Majoranas just because they are these linear combinations of real fermions. Okay, so then the key question that people always wonder is, well, I started off with only real fermions, where's the other Majorana fermion? So there are two. There's one that is actually the one that gives us this 0-point entropy, which is on the local moment site, and it remains unhybridized, so it's the one that's orthogonal to this guy. And then there's another conduction electron Majorana that is not localized on the site, but is fully delocalized throughout the bath. This is at 0 energy. It is a Majorana 0 mode, and if you have more than one of them, it will have Ising anionic statistics. All right, so other properties you can look at is what happens to your various thermodynamic properties. So your specific heat and the spin susceptibility, where I put quotes on the spin here because the model we're talking about is a quadrupolar model. So in that case, the quadrupolar susceptibility is the one that's going to be having this logarithmic divergence. You can also calculate what you expect for the magnetic susceptibility in the quadrupolar model, and it goes like square root of T. Resistivity is expected to have a power law behavior, and that's sort of what you expect from this two-channel Kondo impurity model. You can get this in multiple ways beyond just the Emery and Kibelson. That's sort of the simplest way to show it. All right, and please feel free to interrupt with questions at any time. But I want to talk about what happens when you go beyond two channels, even though we don't have so many examples of these. So we can talk about multi-channel Kondo impurity physics in general with SUN spins, and here I'm using K to label the number of channels, which is essentially the number of ways you can screen these spins. And you can also tune your filling. So we've been mostly looking at like half filling or at a single electron in the quartet or doublet or whatever you're looking at in your SUN. So this is work by Pargalet, Georges, and Gupta and Kotlier, the combination of CFT and large N approaches. And this is also solved in the beta ansatz by Andre and Destry. So what we see is that when, and so I'm going to go through the general case, and then I'll go put some numbers in so we connect to what we're more used to thinking about. So remember, n equals 2 for the usual case. So when k is less than n, that's actually perfect screening in this picture. This picture doesn't capture the underscreening case. So you get a constant susceptibility, which is your heavy polyparamagnetism. Otherwise, you have this intermediate coupling fixed point that is intrinsically critical. It is in general described by an SUN level K conformal field theory. And also there's an SUK level N conformal field, part of the field theory for the channel part. And from this kind of analysis, you can pull out that for K is equal to N, this is sort of minimally overscreened. This is the analog of the two-channel Kondo, so you get a logarithmic divergence in your spin susceptibility. But as you have more and more channels, you get sort of more serious overscreening, and so you get some power law behavior in your susceptibility. And you also generically have a 0-point entropy, which has a complicated formula for generic filling. And I'll give you, again, the examples for a couple of cases. But generically, for these two cases, this 0-point impurity entropy is non-zero. And you can identify from the conformal field theories if there are any, basically, they're not fermions, there are any sort of statistics associated with the states in your impurity. So let's first talk about the two-channel case. This is n equals 2, k equals 2, q equals 1 is the usual case we're used to. So this has a Majorana zero mode. This is also known as an Ising anion or a Z2 parafermion. And so you have two of these, and you exchange them. They have this non-abelian statistics. So here's the behavior we've seen already for the specific heat and spin susceptibility logarithmically diverging. 1/2 kb log 2 entropy, which is also can be written as kb log of square root of 2, which ends up being the quantum dimension associated with the CFT. So now we go to 3 channels. So I'm just changing k to 3. And this gives us Z3 parafermions. So we go from Z2 to Z3, and it will in general be Z sub k. And these are Fibonacci anyons. So they have a t to the negative 1/5, and your impurity entropy has the log of the golden ratio. And these people are very interested in theoretically because while Majoranas, or people talk a lot about Majoranas for quantum computation, they don't actually give you a complete set for universal quantum computation. So if you could realize these Z3 parafermions, you could actually use them to realize universal topological quantum computation. Yes? For which? Yeah, so that was on the previous slide. So this is in this paper. Yeah. So I didn't fill it out. I didn't process this for arbitrary and case. So it has those like signs in it. It's not so clear until you simplify it. And so then I'll just do one more, which is 4 channels. And this is Z4 parafermions. You get a log of square root of 3 for your impurity entropy, and the t to the negative 1/3. And you can look more generally if you have like SU4, quartet, all of this very interesting physics. Then you can ask, okay, but now how can I realize it, right? So I want to just briefly go over the experimental evidence that we can actually have 2-channel Kondo impurities. So the best evidence is in uranium-doped thorium system. So thorium is non-magnetic. Uranium, in these cases, it's uranium-4+, which behaves like it has 2 F electrons. And so this is for uranium, a dilute version of uranium ruthenium-2 silicon-2, which has logarithmic diverging specific heat coefficient and impurity susceptibility. This is along the C-axis, and this is in tetragonal symmetry, so it's one of those doublets where the C-axis is the spin susceptibility. One thing is you don't see the resistivity behavior being square root of t here. It's actually like logarithmic in this region for, I think, most of these cases. Some of them are other power laws or linear in t. But this is sort of an indication. There are some praseodymium materials, so they have less data, but here is the specific heat coefficient for praseodymium iridium 2 zinc 20, which is a cubic material which has, for sufficiently dilute praseodymium impurities, has a linear C over T, or logarithmic C over T. Okay. So one big caveat is that these are all metallic systems. And so while the single impurity case has a Majorana, as soon as you put two impurities, they're talking through the conduction C, and that's critical. So they're going to talk to one another, and they're going to become complex fermions again, essentially. So if you look at these systems, you can analyze, the thermodynamics in a somewhat complex way, but you find that they're not actually consistent with it having a 0-point entropy. So we can see like some of the scaling behavior, but not exactly the 0-point entropy. And that's thought to be because these are metallic systems. So if you could gap it out, which has been proposed by Yashar Kamajani, you could gap out your conduction electrons with superconductivity, and as long as you don't kill your Kondo effect, so you have to have a sufficiently strong Kondo coupling, then you could imagine restoring the 0-point entropy in the Majoranas. He showed this was also consistent with the bosonization picture. Okay, so this is in real materials. There's also a whole other class of realizing multi-channel Kondo purities, which is in quantum dots. And so this is just a little cartoon of, if you have one quantum dot that has a spin, you can have 3 different leads that are 3 different conduction channels. And if you tune it carefully, you can realize, in different cases, 2, 3, and 4 channel Kondo impurity physics in quantum dots. So this picture is about this one. It was taken by this review by Stefan Kirschner, which is quite nice, about 2-channel Kondo impurities. So this is a picture of a quantum dot that has 2 different channels. And if they measure the conductivity, temperature dependence, and do a bunch of scaling, it's consistent with what you expect from the same physics that's giving you the square root of T resistivity. So yeah, so they have these possibilities. They can't still see Majorana physics or parafermion physics here for various reasons that I don't fully understand myself. So it's a good question for quantum dot people. So okay, but these are the possibilities. So I'm going to focus on 2-channel Kondo physics because that's what we get in these impurities. And I'm going to just briefly talk about the possible experimental relevance. And then we'll talk about the interesting new order parameters that you can get that are really quite weird and fun. And then we'll talk about the phase diagram in infinite dimensions and in 1 dimensions, and then sort of conclude by general statements about the phase diagram. So this is sort of the big question that motivates this, right? Your impurity is allowed to have a 0-point entropy, but once you put it in a lattice, it's not allowed to have a 0-point entropy anymore. Something has to happen. So it can do many possible things. It can order, it can form a heavy Fermi liquid, but it has to do so in a way that's actually breaking your channel symmetry, which is what we'll be talking about. So that's sort of the motivating question here. So just to situate you with the possible experimental relevance, we talked about these non-Kramers doublet materials that have sort of an atomic level diagram that looks like this. There's a few proposals, and I'm not going to talk about these in any detail. So this was originally proposed by myself and Premi Chandra and Piers Coleman for uranium, ruthenium-2, silicon-2. It's also been discussed for the praseodymium 1,220 materials, which are known to be 2-channel Kondo systems with this cubic symmetry, non-Kramers doublet. So they have quadrupolar ordering at ambient conditions, but under pressure and field. There's a green square over the interesting red region that's Fermi liquid-like. Not sure where that came from. But at any rate, there's possibilities that if you tune these, you can get unusual orders. And there's also thulium selenide, which is a mixed valent 4F12 to 4F13 system that has a Kondo hybridization gap opening at the Fermi surface or Fermi level that could be also associated with this physics. So just to give you a sense that this could be possible, it's also been discussed if instead of, we have this, we just flip it, that also gives you two-channel Kondo physics. This was proposed by Dan Cox to explain uranium beryllium 13's unconventional superconductivity, and possibly you're tuning the relative valence as you do thorium doping, and there's a superconducting dome. It's also been discussed when you have two Kondo channels that are not generically the same. One is going in this direction, one is going in this direction, they have different symmetries. That can give you composite pair superconductivity, which we'll talk about, and that was discussed for the cerium, cobalt indium 5, cerium rhodium 5, cerium rhodium 5 materials. All right, and I think it has potentially broad applications. So we've seen recently a lot of sort of engineered Kondo physics. So with Kondo heterostructures, like the tantalum sulfide systems, the transition metal dichalcogenide systems, and also not so engineered, but engineered by theorists, this topological flat bands in twisted bilayer graphene and many other systems. So it's possible you could engineer not just single-channel Kondo physics, but two-channel Kondo physics, and then this would be relevant in a whole new class of materials. So now let's talk about what we actually know about the physics of the two-channel Kondo lattice. So here's the Hamiltonian. This tau I'm using to describe this ground state doublet, and we're assuming that we're at degeneracy. Okay, so we can do a few things here. So we can solve this exactly in the large N limit. There's two different large N limits that you can do that give you two different types of physics. And I'll talk about this very, very briefly. You can also treat it numerically, either in one dimension using DMRG, which is going to be my main focus, or in infinite dimensions using DMFT. In between, there's some results using other numerical techniques, but not a whole lot. It's a very difficult problem, has a sign problem, for example. So the proposed phases here is you can have ordering of your spins, which is what I'm using to call this ground state doublet. So it's ferromagnetism or antiferromagnetism or something like that. But if your ground state doublet is quadrupolar, then it's actually ferro-quadrupolar order or antiferro quadrupolar order or octopolar order. But some ordering of this ground state doublet. And hypothetically, you could have large or small Fermi surfaces with heavy fermion physics here as well. The interesting new thing that you can get in the two-channel case is that you can have a channel ordering. And so if you want to form a heavy Fermi liquid that's your ground state, you actually have to break your channel symmetry. And so this is a channel symmetry breaking heavy Fermi liquid or a channel symmetry breaking Kondo insulator. Hypothetically, it could also be a non-Fermi liquid, and there are some indications that that might be true. We call this hastatic order because it's a lot shorter and more fun to say. And it was also, I don't have the reference currently, talked about by Hoshino et al. As diagonal composite order. Okay, so that's what I'll spend a good bit of time talking about it. But next, I just want to say the next thing you can have is composite pair superconductivity, which is basically forming a heavy Cooper pair by having your conduction electrons in two different channels trying to screen the local moment. And again, I'll talk about that in a minute. And then you can have disorder phases. You have paramagnets, you have non-Fermi liquids. Basically, it's a very rich phase diagram. Anything you can get in the one-channel Kondo lattice, you can get here, and then more. All right, so these are the two unusual phases that I want to talk about, because those are unique to the two-channel Kondo lattice. So let me just refresh the sort of usual single-channel picture. So here was the Anderson model for Kramer's doublets, and what we'll often do is say, I'm going to forget about this guy. So I'm going to take U to infinity and remove the double occupancy. So this is now the infinite U Hubbard model. And these are no longer fermions because they don't have any double occupancy. So I need to represent them with Hubbard operators. So this is just a Hubbard operator representing the F1 state, which has a sigma label. And this is a Hubbard operator representing the F0 state. So the hybridization has these terms, and chemical potential has these terms. So then we can represent these using an auxiliary particle mean field theory, where we use bosons to represent the excited state and fermions to represent the F1 state. And so once we do this, we can represent any kind of combination that shows up in our Hamiltonian using these slave particles. And we also have to impose a constraint that we're in this sort of physical subspace where we're either having this empty state or we're having one of these two singly occupied states. So the number of bosons plus the number of fermions must be 1. And so we can then, so I plug these in and I put the constraint in here. And oops, there's an extra prime that shouldn't be there. And then I can go to a mean field picture where I condense my bosons. This is what I expect to happen at low temperatures. So now I have an emergent hybridization that's the bare hybridization B times this expectation of B here. And this shows up in my constraint, and now this is a nice quadratic theory that I can diagonalize, and it gives me that picture I showed you yesterday of the hybridized bands. Okay, so that's the single channel case. So I'm gonna just put this up again in the same cartoon and then modify it for the 2-channel case. So we're using this auxiliary boson to represent the excited state. There's only one of them. It's because our excited state carries no quantum numbers, so our hybridization breaks no symmetries and develops as a crossover. Okay, but now we have our non-Kramers doublet. This always fluctuates to a Kramers doublet. So I don't have just one excited state, I have 2. And so I need 2 bosons to represent these. And this is a half-integer spin state. So this is should be represented as a spinner, right? So I package these bosons into a spinner. And so I'll use them like B up and B down to represent these 2 states here. And so this is when we get the 2-channel Kondo effect. So since our excited Kramers doublet is carrying a magnetic quantum number always, the hybridization breaks time reversal. It develops as a phase transition. And it is spinorial in some sense, and we'll talk about what that really means. So this is weird. It means you have a phase transition where your hybridization is turning on because you're breaking a real symmetry. And so this is the idea. And you can talk about your order parameter as essentially being the magnetic. So your order parameter is really this guy that's condensed. And the main feature is that there's a little tiny magnetic moment that is in your excited state below this hastatic ordering temperature. So this is what we call hastatic order. Okay, so good. All right, so now we go back to the model that we wrote down, but I put a bunch more indices because this is now representing our 2 Kondo channels. So I have this label M for the channel. I go to infinite U, I introduce my Hubbard operators, and then I introduce my mean field theory. So I've skipped a bunch of steps. But the main change is that I just have, K flavors of bosons, so 2 for 2 channels. I have 2 flavors of these bosons that are representing my 2 excited states. So then it proceeds very similarly to the single channel mean field theory. There's just more indices, so there's more fermions around. And more bosons, so more possibilities. Okay, so let's talk about what we get if we look at the order parameter, which is this little tiny excited moment. So this is the excited moment in your F1 state. So this is called the composite order parameter, and shortly I'll write it down what it looks like in just the Kondo model limit. But it's basically choosing which channel in which to form a Kondo singlet. So here's my cartoon that I have. My local moments are represented by a dot. I have my 2 channels that are up and down, and this kind of oval represents a singlet formed between the F electron and here are the up induction electrons. So this is generally an SU2 spinner. It's just easier to look at the Z component, which is what we're doing here. If anyone has any questions, please interrupt at any time. So this is what it looks like just for 1. Then when you arrange it on a lattice, you have choices, right? And you have basically all of the choices that you have for magnetism. And in fact, this behaves like a tiny magnetic moment, so it has all the same symmetries as a SU2 magnetic moment. So you can form, we call ferrohastatic order, where they're all aligned. And in this picture, I'm also allowing f electron hopping, because that turns out to be important just to fully understand the physics in this model. It's generically possible, actually, Fokker showed it yesterday, where you get from the RKKY coupling or Heisenberg coupling, you get an FF type hopping term. Okay, but this ferrohastatic order is just saying I'm only screening my local moments with my up channel of conduction electrons. And so this breaks channel symmetry like a ferromagnetic moment. You will have tiny ferromagnetic moments, but they're suppressed by TK over the bandwidth, so they're very hard to measure. And what you get is a half heavy Fermi liquid, right? So one channel, these reds are forming a heavy band that's opening up a hybridization gap, and one channel is remaining decoupled. So this is what your band structure looks like, for example. And there's a bunch of signatures that I'm not going to focus on today. The other possibility is that you can form something like an antiferromagnet, so antiferrohastatic order, where you're saying, well, I'm going to have two sublattices, and sublattice A is going to hybridize with the up electrons, and sublattice B is going to hybridize with the down electrons. So this gives you a fully hybridized heavy Fermi liquid, and it has a staggered broken channel symmetry like an antiferromagnet. But actually, it's a little bit more difficult because this is a spinor order. So just, in the large N limit, our order parameter really is this expectation of B, which is a spinor. And we know that time reversal acts differently on spinors than it does on vectors, which are our usual order parameter vectors. So spinors have this time reversal squared as -1. So usually when we have an antiferromagnet, we say on sublattice B, it's just the time reverse of sublattice A. So we can do that here. So on sublattice B, I put the time reverse of sublattice A. But then if I want to, say, keep going, I could make sublattice C the time reverse squared of sublattice B. That picks up a minus sign, which ordinarily doesn't matter for quantum states, but here it's a difference between two sites, so it does matter. So this is just negative BA. And I need 4 sublattices, basically, to get back to my analog of antiferromagnetism, where I have an anti-unitary symmetry that acts like time reversal. So in that case, it's basically time reversal plus moving along your 4 sublattices. Okay, so here is this cartoon of this 4 sublattice order. Note that these 2 pictures, they look the same with where my Kondo singlets are distributed. So this order parameter is actually the same for both of these, because it's just telling me I'm hybridizing with ups on the A's and downs on the B's. The difference between these two is that these 2 have a really tiny plus sign on them, and these 2 have a really tiny minus sign on them, and then it repeats. Whereas if I just do the naive thing of just putting in the staggered orders with all the same sign, this actually breaks time reversal symmetry, but only through these phases here. So this is really weird, but they're really breaking 2 different symmetries. So like in 1D, this breaks inversion symmetry. There's no center of inversion, whereas this breaks time reversal symmetry. And you see the signatures of both of these broken symmetries in both states, which are both possible allowed states. Okay, and this is an additional broken symmetry compared to the sort of broken spin rotational symmetry and broken translation symmetry in the between the A's and B's, and that comes from the fact that we originally had a spinor. Okay, so why? Let's talk about this in a little more detail. So in the mean field, this is just sort of, it's obviously a spinor, but then you're like, okay, but we don't live in the mean field, and our B's actually have a gauge dependence, and much like the regular slate bosons in the single channel Kondo effect, so they don't order for any finite n. But we have these 2 staggered orders that have the same composite order parameter or distribution of these singlets, but different symmetries. So something must be going on. The only difference between these 2 is the phase of the spinor. So let's talk about some putting back up here the mean field Hamiltonian, and I've added now an F electron hopping term, which, as I said, comes generically from RKKY or Heisenberg terms. It looks, I call them F electrons. Again, remember that this, until they hybridize, they're spin-ons. Essentially, they're neutral particles. So this is like a spin liquid term. Okay, so this expectation of Bj is an SU2 order parameter. And so it generically will have this kind of form where you have angles and you have an overall phase, and you can look at the sort of ordering possibilities of this. And you also have an immersion gauge symmetry. So if you take this Hamiltonian, before I do the mean field, and I take my bosons to have this phase, I take my fermions to have this phase, and I take my F electron hopping term to pick up this phase as well. This is the symmetry of the model. This is this emergent gauge symmetry, and it's these gauge fluctuations that will kill this expectation of B when I go beyond the larger limit. This is known as Elitzer's theorem. So this will kill this expectation value, but what it won't kill is any gauge invariant bilinears. So I have 3 of these in general. So I can have just a change in valence. This doesn't break any symmetries generically. I could have it be different on different sites, but usually we don't guess that that's the case. I have this composite order parameter that we looked at before. This is a local symmetry breaking order parameter. It behaves like a magnetic order parameter, has all of the usual properties of an SU2 magnetic order parameter. But now there's something else, which is this guy. And so he comes from having F electron hopping, and this hopping, essentially a spin-dependent hopping of these B's from site to site. So this is a non-local order parameter. It's coming from the spin liquid, so it has a lot in common with a spin liquid order parameter. It is an indication of fractionalization. This is where the time reversal symmetry breaking comes from if you have the 2 sublattice order, as you get a scattering of your conduction electrons coming in and scattering off of site A into an F electron that travels to a sublattice B site and then comes out with the opposite spin. Okay. And this is gauge invariant under this gauge transformation. So it should be allowed to survive beyond the mean field theory. And what I'll show you is that we actually see evidence for this in DMRG. So it really exists. Okay, any questions at this point? Just gonna give you guys. All right. So it will be useful later to write these in terms of just the real original particles that we have in the Kondo model, so conduction electrons and spins. I put in all the indices just to, which maybe makes it more clear, maybe makes it less clear. But this is a conduction electron. It's the formation of the Kondo singlet, essentially, between your conduction electron moment dotted into your F electron moment, and then choosing the particular channel that you're operating in. Then this non-local order parameter is defined between 2 different sites. Usually we just look at the nearest neighbor term, and this is a triple product of your spin on one site, your spin on another site, and a conduction electron spin flip hopping term in between the 2 sites. So it's somewhat complicated, but again, this is what actually just shows up out of the model. And it's really all coming from the spinorial nature of the order parameter. It's just whenever you actually measure it, it's not really the spinor you're measuring, it's 2 different vector order parameters. All right, so when we go beyond mean field theory, or rather, let me say, first, when we do mean field theory, all of this just shows up. They all order all at the same time. We break all of the symmetries. When you go beyond mean field, we don't have that constraint anymore. So you can develop things at different temperatures. So this is just a generic Landau phase diagram. If we have temperature on this axis and some kind of tuning parameter that could come from your microscopic theory, so you can order your amplitude of your spinner first. This doesn't break any symmetries, so it can develop as a crossover. There are some hybridization gaps associated with this. You can order your spinner on the site, which behaves like a magnetic order, or you can order this inter-site interference term, which is the spinorial order, and both of these break different symmetries, and they can in principle turn on at different times. And if you cool down, the second phase diagram generally, or second phase transition generally has a really tiny specific heat jump. We looked at this in the paper that's not on this slide, but is cited on other slides. So, good, okay. So that's sort of the basic phases that you can get. So now I want to talk about, do we get these, right? This is the possibilities. So here, this is what we get in the large N limit. This is solved in 2D, where I put on a Heisenberg RQKY coupling, and you get, just to capture a little bit richer phase diagram. And you see all of these possibilities that I discussed. There are actually two-dimensional versions that look a little more complicated than this, but they have the same basic properties, where you have 2 sublattices, 4 sublattices, ferrostatic, and then there's some staggered phases that don't have this F electron hopping, so they don't have a difference between 4 sublattice and 2 sublattice. So they all show up. That's really my main point. And I should note this is valid in the SU N limit, which I think is a good approximation for non-Kramers ground states. You can also do an SPN limit, which is what's looked at in this paper by myself, Maxime Zero, and Piers Coleman. And this is, okay, so SU2 is SP2. And so as you take N to infinity, you could either go SUN or SPN, which is generally a subgroup of SUN that has a well-defined time reversal symmetry. And so that works better if you're trying to describe superconductivity. And if you pick that limit, you get only composite pairing. If you pick SUN, you get only static orders. And so the large limit doesn't really tell you much about which one is gonna win. Okay, so let me tell you about composite pairing quickly. So to give you the brief picture, I'm gonna go back to this idea of composite fermion. Oh, yes.
Go back to the former slide. Half filling, this is something like you would want to.
Yes, and it totally disagrees, right?
Well, no,
oh.
So for the SUN,
Oh, for SUN, that's true. It should agree. Okay. Yeah, no, I don't know that it's been done. Okay. That's a good question. Yeah. So this this ferrostatic phase, that's also what Piers proposed in this Wugalter et al. Paper. Yeah, I will show that very soon. Okay. So good. Okay. Any other questions? All right. So I just want to talk about. Okay. So composite pairing is a new thing you also get in the 2-channel Kondo model. So I talked about composite fermions yesterday, and this is sort of the basic idea is that it's a new way, a new fermionic excitation in the heavy Fermi liquid, where if you want to tunnel an actual electron into your heavy Fermi liquid system, one of the ways you can do it is by flipping a spin as you're adding the conduction electron. So the conduction electron flips, the spin flips, and this combination is your composite fermion that has a spin 1/2 degree nature, essentially. So you get another possibility in the 2-channel Kondo where you can actually add a triplet pair of conduction electrons to your system by flipping the local moment. And this combination of this triplet pair of conduction electrons, which has to be in 2 orthogonal Kondo channels, is then gonna combine with a spin flip to give you something that's a spin singlet pair. This was originally proposed as odd frequency pairing by Abraham, Spalatsky, Scalapino, and Schrieffer. Good, okay. So the basic idea is that the composite pair is a singlet. You need a triplet pair of conduction electrons. So it's sort of symmetric. It's anti-symmetric. Sorry, that's incorrect. The spin is anti-symmetric, so it must be symmetric spatially, but you need these 2 orthogonal channels. That's the main point here. And you can also write it this way, which will show up later, but it's just a generalization of this to be sort of more accurate with the SU2 symmetry. So we can go back to a two-channel Anderson model to see what this looks like in a real system. And so here, this is in tetragonal symmetry. If you have this ground state crystal field symmetry, and you have this excited state crystal field symmetry, one of the possible doubly occupied states is a singlet that's combined by adding this gamma 6 to this gamma 7. And so that gives you that this channel has symmetry gamma 7 that looks like this, and this channel has symmetry gamma 6 that looks like this. And note that this is an hole-like Kondo coupling, and this is a electron-like Kondo coupling. So in the Kondo limit itself, that doesn't really matter, but in real life, we're not exactly in the Kondo limit, so it does end up mattering. And the possibility you get here, this is the mean field phase diagram for this case, is that if your two channels are different, you're either going to form a heavy Fermi liquid in one channel, which is screening your local moment with holes in the gamma 7 picture, or in the other channel, which is screening your local moment with electrons in this gamma 6 picture. But in between, you have sort of a resonant Kondo screening where it isn't really sure which one it wants to do, so it goes back and forth, and you end up with an interference term here that actually gives you D-wave pairing. That is peaked very strongly where you have the two-channel Kondo degeneracy. Okay, good. So now let's talk about what we actually get in the system, right? So I can make up all the phases I want, and I can get them in a mean field theory. This is something you can always do. You can have lots of fun, but at some point you want to come back to reality. We can't actually go back to reality, so we go as close as we can do, and we do it in infinite dimensions, let's say. So this work was done by Hoshino et al., who's done a lot of work looking at this two-channel Kondo lattice in DMFT. And so this is a phase diagram versus conduction electron filling and temperature. And they find, let's see, antiferromagnetism at half filling. So the total filling is 4, because there's 2 channels and 2 spins. So they find antiferromagnetism. They find ferromagnetism at low filling, much like in the single channel Kondo. They find a composite pair superconductivity that's actually staggered between sites at this sort of region here. And they find this antiferrohastatic order here around quarter filling, which is also where it showed up in the mean large N limit. And finally, they find this metastable ferrohastatic order around half filling. But you see that the antiferromagnetism always wins. But the other phases are composite pairing and antiferrohastatic order are really there in the infinite limit. All right, so we don't live in infinite dimensions. We also don't live in one dimension, but the idea is if you look at both of them and you have phases that exist in both, maybe those exist in 2 and 3 dimensions, which is what we're really interested in. So here I'm showing the original density matrix renormalization group, which was done in 2005. And that motivated us to look again once we understood what is possible in two-channel Kondo physics. So here, they're tuning the conduction electron filling. This is now as a fraction of the total filling, so this is still half filling. This is the Kondo coupling rescaled by J plus T, which is the conduction electron hopping. And what they find here is a little hard to read, so I'll just interpret. This is ferromagnetism for less than quarter filling. They find antiferromagnetism exactly at quarter filling for weak coupling. They find a staggered channel order, which is antiferrohastatic order exactly at quarter filling. And then they have a bunch of other paramagnetic states that they don't give you any information about. And that, there's also, they even find a paramagnetic state at half filling. So we came at this and thought, well, okay, they found static order at quarter filling. That's already really cool. That's where it's an insulator, so it's particularly stable and easy to find. But there's been a lot of progress in DMRG studies of Kondo lattices, and with iTensor, it's very accessible for people who don't necessarily do DMRG normally to start doing it. So we wanted to look at, is it really static order only at quarter filling? Can we see what phases are heavy, which had not been looked at yet for this two-channel Kondo lattice, and can we see the spinorial nature? All right, so we looked at this in DMRG, where these are the numerical details. We looked at the ground state correlation functions in real space and Fourier space and found the following phase diagram, which agrees with their information everywhere, but we just find a lot more. And that's basically because we knew what we were looking for. So we find static order in basically everywhere. I should note this is one dimension, so it's all algebraic orders, but it's very strong correlations. So this is what we get, and let me go through it fairly quickly. So we can look at this composite order parameter, which is essentially, if we look at just the z component, this is how much Kondo singlet we're forming in the up spins and how much Kondo singlet we're forming with the down spins. And so we can look at, this is in this region here, the correlation function of this static order parameter, composite order parameter. We see that it oscillates, but has this envelope that goes like 1 over x, which is a very strong power law behavior. And you can Fourier transform this to find the Q dependence. And in this red region, we find this Q dependence depends on the conduction electron filling. And we find that all of the spins are totally screened. It's S equals 0 state and has this composite order with a Q vector here that varies between pi to 0 as we go from quarter filling to half filling. Okay, we can look at the nature of the metallic states. First, we see there's no charge or spin gaps. You can look at then the Fermi wave vector by looking at non-elasticities in the conduction electron momentum distribution function. You can also look at the spin charge and superconducting correlation functions and a bunch of other things. So here is the non-elasticities in the conduction electron momentum distribution function in this red region for a couple of different fillings. And we see that there is a non-elasticity at this KF star, which is associated with the static density wave, and not at the light Fermi wave vector. Yes? They're heavy. Yes, so they are all, okay, so these phases on the quarter filling and half filling are not, they have charge gaps. But otherwise they are Luttinger liquids. We can show, and I'm blanking on the details right now, we can show that these phases are Tomonaga Luttinger liquids, whereas it's hard to tell for this one, it might not be. And if you ask me afterwards, I'll remember what the details were, but my student did that somewhat recently. Yeah, for these heavy regions, you can really look at what your wave vectors are, and there are different places. You can look at the Luttinger parameters, and I'll show some of that later as well, if I get to it. Okay, so you see this main non-elasticity up here, and we can look at this in a mean field if we know what kind of what our density is and what Q vector we expect to get. So this is the same mean field as before. I'm going to just go through it really quickly. You get a band structure. So at 1/3 filling, this is probably really hard to see, but you have these dashed lines are your conduction electron light wave vector, and the thicker lines are your heavy band structure. The blue line is your Fermi wave vectors, Fermi level. So you see several different crossings. You can do it for 3/8. You can do it for 7/16. It gets complicated. There's always one pinned at pi/2. And this is coming from the sort of dependence of Q on MC. And we don't actually measure the heavy bands. We only looked at the conduction electron density. I don't know if in DMERG you can actually look at the composite fermions, but at any rate, in our mean field, we find this. Oh my goodness, the 1/3 is not visible. But the 3/8 has just one jump. The 7/16 has a jump here. The 1/3 has a jump here. And these match up with the non-analyticities here and here and here that are very hard to see. But it agrees, right? So we get a mean field jump in the conduction electron density, and that corresponds to a non-elasticity in the DMRG. So we really believe this is describing this static density wave. All right, so then I can look at this ferromagnetic plus static density wave region. So here, not all of the spins are screened. There's essentially not enough conduction electrons to fully screen the local moments here. So NC spins are screened, 1 minus NC spins remain as a ferromagnetic state, but the NC spins that are screened join the heavy Tomonaga Luttinger liquid with this KF star that goes like 2NC that you can see as you sort of move along. And you can see that more and more spins are incorporated into your Fermi surface as you move this way. Okay, finally, we also see this incommensurate antiferromagnet, which does not incorporate the spins into it. It's a small Fermi surface, so you can see the sort of weak non-analyticity at the light Fermi wave vector that you expect. All right, so this is, I think, the most interesting thing to me is that we can also look at this additional order parameter, this phi, where we've looked at nearest neighbors. And so these are the correlations of phi along the chain for quarter filling and 7/16 filling. So the quarter filling behaves like kind of like 1 over x cubed and is uniform, whereas the 7/16 has a staggered and behaves like 1 over x. You should note that this is much smaller than the composite order parameter, but it is clearly there, and it is a strong power law. And so this is a Fourier transform for a few different values. It has the same Q dependence, except for the uniform component as the static density wave. So it's much smaller magnitude, right, 1 over x. In the Kondo insulator, it's uniform and has a subleading power law behavior. And this is also cool because in the 2-channel Kondo lattice model in the mean field, if I don't add a Heisenberg term, I don't get this term. And I don't have a Heisenberg term in this DMRG model. So this is essentially showing that there's evidence of RKKY physics in this system. Okay, and then this I think is also very interesting, which is we know that the 2-channel Kondo model impurity model is critical. In 1D, we have a heavy Luttinger liquid. There's no Fermi liquids, but we can get a sense of whether or not we're behaving like the single-channel Kondo model, where as we get closer and closer to strong coupling, we look more and more like a Fermi liquid. Or what we do here is it's actually the opposite. So you can look at the charge Friedel oscillation. So this is a lattice with open boundary conditions. So you have Friedel oscillations that have this kind of dependence on Fermi wave vector and the Luttinger parameters. And so you can use this, these 2kF and 4kF jumps to extract the Luttinger parameters as a function of J. What you see, we don't have a whole lot of points, so I'm not plotting it as points, but in the single channel model, you find that this Luttinger exponent K increases with J, and that corresponds to decreasing residual Fermi liquid interaction, or residual interactions in your Luttinger liquid, or what would be residual interactions in your heavy Fermi liquid. Whereas here, we find that K is decreasing with increasing J. So we're finding increasing residual interactions as the J is increasing. So this is suggestive that this is not just a normal going to a heavy Fermi liquid. So when we go to higher dimensions, it might be a non-Fermi liquid instead of a Fermi liquid, in addition to the static order. All right, so I should just say we don't find composite pairing. We looked for it. And so that leads me now to my conclusions, which is what we know about the 2-channel Kondo lattice. So in 1 dimension, we find that algebraic static order, if you have strong enough coupling, you basically always have that, except at this one point, which you can solve exactly in quantum Monte Carlo, where you have antiferromagnetic insulating order. But we find that they're heavy, all of them. We don't find composite pair superconductivity in 1 dimension. It's exponentially suppressed. And we do see evidence of residual criticality. and evidence for spinorial order. So what we know about higher dimensions, we have this DMFT results, which do show composite pairing. Notice they show antiferrohastatic order here, around here. So it suggests that if you're near a quarter filling, you expect this antiferrohastatic order to survive. I mean, if it's there in one dimension, it's there in infinite dimensions. It's probably there in 2 and 3 dimensions, especially right at quarter filling where it's an insulator and particularly stable. Composite pair superconductivity shows up at some point as you go to increase your number of dimensions. And there's indications that hastatic phases might be non-Fermi liquids in this paper by Inui and Matome, where they looked at channel selective non-Fermi liquids in magnetic field. So this DMRG study is in this paper, and that I just want to acknowledge all of the people who I've worked with on this problem over the years, and a lot of the stuff we talked about here is in the following papers and was supported by this DOE grant. So thanks very much, and I'll go back to my conclusions if people have questions.
So I had a question about how one can distinguish the foam liquid that you get in a single channel Kondo model versus the foam liquid you get from a perfectly screened case of a multi-channel Kondo.
I don't think there's going to be, I mean, okay, so a perfectly, so, okay, so when you say perfectly screened, we don't really call it it is multiple channels, but the number of channels is equal to the spin degrees of freedom. So this is not really different than just like SUN Kondo physics, which we still call single channel. So you can distinguish SUN from SU2 if you look at like the Katawaki-Witz ratio and a couple of things like that, but it's not a, otherwise it has all of the same basic features.
So basically, the specific heat, the susceptibility, and they're all the same.
They're all Fermi liquid-like, yes. Yeah. Yeah.
What are the steps to go from these results to realistic to a three-dimensional?
Yeah, so you can do a couple of things, right? So you can be more realistic in mean field and take what your actual hybridization functions will look like for a particular lattice with a particular non-Kramers doublet and conduction electrons, and use that to figure out what your band structure would look like, what actual symmetries are broken. And this is what we did for uranium, ruthenium, silicon 2 in a few papers, and for some of the praseodymium 1220 materials. You can also try to look at it in something like DMFT. If you want to look at the broken hastatic order, you need to maybe look at like cluster DMFT if you want to do something like that. But as far as I know, people have done DMFT looking at the two-channel Kondo physics, but not allowing it to break the channel symmetry. And so there, generically, you get non-Fermi liquid physics. So this is done by Cox and also by Chimnow's group and recently. Yeah. There's one back there.
Any comments about the property or its quantity of the lattice on the finite division? Anything we can simulate, like the entropy or the specific heat?
Yeah, I don't know. That's a good question. Yeah, I don't know. So I'm somewhat new to DMRG, so I haven't thought about trying to do finite temperature. Yeah. Yeah. Oh, with Monte Carlo. Yeah, so that might be really interesting, actually, to see if there's... Oh, there's no sign of it. Wait, what? Okay. All right. Maybe we'll come back to that discussion at lunchtime.
Just very quick question. So this channel selective
Yes.
is it just not just very briefly on that?
Yeah, so, okay. So when you have the non-Kramers doublet that is the quadrupolar doublet, and then your channel is just the spin degree of freedom. You put it in a magnetic field, you break your channel symmetry. And then you can actually get, so if you start off not wanting to be in static order, but you turn on magnetic field, you might want to be in the particular static phase that is aligned with your magnetic field. That's what you get from like sort of the mean field picture. And then they looked at something basically similar where they were simulating this two-channel Kondo lattice in magnetic field, where the channel is breaking the spin rotation symmetry, and they found a dome of non-Fermi liquid physics where only like the spin up electrons that were hybridizing had non-Fermi liquid signatures, and the spin down electrons that were not hybridizing were normal Fermi liquids. So the ones that were basically forming the heavy, what would be a heavy Fermi liquid if it were a Fermi liquid, were a heavy non-Fermi liquid, essentially.
Something that cannot be seen in the purity models?
Well, I mean, I guess no. Yeah, so when you're looking at the impurity model, as soon as you're breaking the channel symmetry, you have a Fermi liquid. Now, I think this is a finite temperature, so it may be that you've like broken the symmetry enough to favor the phase, but maybe not enough to mean that you're out of the quantum critical region. I did a little, so my picture where I draw the quantum critical region looking like this is a little bit of a lie. It looks like this. It's like parabolic. So it could be that you're still in that region where you're just seeing the finite temperature residual criticality, or it could be that when you're in the lattice, even if you're sort of you're very weakly breaking the channel symmetry because the moments are not very large. So
Yeah, maybe the constant export is very large.
yeah, possibly. I don't know. It's a good question. All right, I suspect you want us to wrap up. So